In 1815, a mysterious veil of dust began to spread over the Earth. The culprit was a remote East Asian volcano, Mount Tambora. It was the largest eruption in modern history, spewing out 80 cubic kilometers of debris and taking up to 100,000 lives. But even this was just a fraction of what Earth is capable of. Supervolcanoes, like the ancient eruption of Mount Toba in Indonesia, can unleash 50 times the power and 30 times the amount of debris. An eruption of this scale today would be catastrophic, potentially claiming up to 1 billion lives. There are about 20 active supervolcanoes on Earth today, sleeping beasts that present an even greater threat than asteroid strikes. Instead of waiting for them to explode, what if we could steal their energy and use it for ourselves? One NASA engineer has a proposal for exactly that. The idea is to drill a series of boreholes several kilometers deep around the outside of the magma chamber. Cold water would then be injected down into the rock, become superheated, then get pumped back to the surface to carry the heat away, gradually cooling the magma. The location of the boreholes will be critical. Drilling too close to the chamber itself would risk triggering an accidental eruption. But if done right, the superheated water removed from below would provide a continuous source of renewable energy. And over tens of thousands of years, the energy removed may eventually be enough to cool the chamber completely. To fully protect civilization, we will have to neutralize not just every existing supervolcano, but all future ones. Magma plumes from Earth's mantle are continually bubbling to the surface. These plumes will continue to trigger supervolcanic eruptions as often as every 50,000 years. Learning to harness these forces could mean the difference between catastrophic collapse and the long-term survival of humanity. But it's not just supervolcanoes we will have to manage. From the lithosphere to the atmosphere, each of Earth's layers are prone to shocks that can threaten civilization and life itself. Our job is to protect and manage these layers with the power of technology, to build a safer, more livable planet where life and humans can thrive together for millions of years. And creating a safer planet starts with creating a safer climate. In 1991, the eruption of Mount Pinatubo ejected 20 million tons of sulfur dioxide into the stratosphere. Reflecting sunlight around the world, and causing global temperatures to fall up to 0.5 degrees Celsius for nearly 2 years. The cooler temperatures even slowed the pace of sea level rise for the next decade. With global temperatures and climate catastrophes on the rise, this event inspired a bold idea. Artificial volcanic eruptions. Like putting sunscreen on the Earth, spraying sulfur dioxide high in the stratosphere would reflect sunlight and temporarily cool the planet. A single ounce of sulfur dioxide in the stratosphere can offset the warming effects of several tons of carbon dioxide for a year. Dusting the sky would have an immediate effect, buying us time to decarbonize the global economy. But there's a catch. The exact effects may be unpredictable and uneven. Weather patterns could become erratic and threaten food supplies. With so much at stake, the fight for control over Earth's climate could even escalate into armed conflict. A team at MIT has developed a concept for a giant solar shield out in space, thousands of kilometers across. Placed where the gravitational pull from the Sun and Earth balance out, it could reduce sunlight by 1.8%, just enough to bring temperatures down to pre-industrial levels. The shield would be made of silicon bubbles, inflating out in space to ease their transport, and deflating if the solution needed to be reversed. To block enough sun, this solar shield would have to be absolutely massive, about the size of Brazil. Others have proposed systems of space mirrors to precisely redirect sunlight, which could be used to increase solar radiation if temperatures drop too low in the future. Large-scale ecosystem engineering can go a long way in securing the stability of Earth's systems. In 2007, the United Nations launched the Great Green Wall Initiative, a huge effort to plant a 5,000-mile belt of trees across the entire African continent. This vast new forest will not only suck up 250 million tons of carbon, but also combat desertification, increase food security, and create millions of jobs. Managing our planet effectively will require forging deep alliances with the biosphere. That includes preservation of natural carbon sinks like the Amazon rainforest, which are a critical ecological counterweight to human activity. But in some cases, that may also mean bioengineering new forms of life itself. By tweaking the machinery of photosynthesis, scientists have recently created plants that grow up to 40% larger than their natural counterparts, hinting at a future of radically enriched crops and plant life. They have also begun to engineer algae that convert sunlight into clean-burning hydrogen fuel, and microbes that have been reprogrammed to generate electricity from mud and wastewater. But most dramatically, we are now on the path to creating a hybrid woolly mammoth by tweaking the genes of Asian elephants. These creatures could be reintroduced to the Arctic, where they would help keep the permafrost frozen and prevent billions of tons of CO2 from leaking into the air. Genetic engineering could become our most potent tool for managing the planet, maintaining ecological balance and making the biosphere more diverse and resilient. The wonders of the future may not be built with concrete or circuits, but with cells. These are mechanical trees. They mimic the real thing by soaking up carbon onto special plates that act like leaves. Once captured, the carbon can be buried or recycled, and the cycle repeats. A single one of these machines can sequester as much carbon as 1,000 living trees. Vast forests of artificial trees could be deployed in inhospitable regions. And with 100 million of them, we could offset our entire carbon emissions. Excess carbon dioxide in the oceans is weakening food chains by causing the water to become more acidic. Pulverizing a part of barren seabed would allow rock particles to soak up the excess CO2 and restore balance to the waters. A single nuclear bomb placed 5 kilometers beneath the seabed could shatter enough rock to sequester 30 years of carbon emissions. The bomb would have to be massive, potentially over 1,000 times more powerful than Tsar Bomba, the largest nuclear bomb ever dropped. But the deep sea water pressure would contain the blast and minimize fallout. The best location could be the remote Kerguelen Plateau, where the seafloor is mostly barren and rich in basalt rock. This is geoengineering at its most extreme and most dangerous. But preserving the oceans and millions of human lives makes even the most extreme ideas worth considering. For a safer way to manage the seas, we don't have to go far from shore. Artificial reefs, built from sunken ships and man-made materials, can become bustling marine cities, with some studies showing fish abundance increasing up to 20 times compared to bare seabed. Widespread artificial reefs could boost the ocean's natural carbon drawdown by offering habitats for trillions of corals, shellfish, and seaweeds that capture carbon during their growth. On a massive scale, these reefs could offer powerful natural defenses, reducing erosion and storm surges by absorbing wave energy. But managing our planet's hydrosphere is about more than protecting our oceans. It means preserving the glaciers and ice sheets that cool the world and hold back rising seas. This is the Thwaites Glacier in Antarctica, a massive ice sheet that spans 75 miles. Rising ocean temperatures are causing warm oceanic currents to wind their way underneath the glacier, causing it to crack and destabilize. If it collapses into the sea, it could trigger up to 10 feet of sea level rise, flooding coastal cities around the world. To avert disaster, a geoengineer at the University of Lapland has a bold plan. The idea is to construct a massive 100-kilometer-long underwater curtain around the glacier, designed to block warm ocean currents from reaching the underside of the ice. This vast undersea barrier would be engineered to withstand collisions with icebergs and could be removable if problems arise. At the opposite pole of the planet, ambitious proposals are being made to stop the loss of Arctic sea ice. Vast fleets of wind-powered pumps could draw seawater to the surface during the winter and spray it over the Arctic surface, where it would rapidly freeze in the frigid air. An American architect has recently designed a polar umbrella, which would float in Arctic seas using solar power to harvest seawater and create new ice. Deployed in the fastest melting regions, these umbrellas would cast a cooling shade that would lower surface temperatures and rejuvenate the Arctic ice. But most of these grand solutions have a common problem. They each require enormous amounts of resources and energy. Where do we get the power and materials? And how will the insatiable demand for energy shape Earth's future? For the last 2 centuries, our energy use has been growing exponentially, surging over 7,000% and fueling a 100-fold increase in global economic output. Continuing this level of growth will eventually require generating hundreds of trillions of additional watt-hours every single day. But thanks to revolutions in solar power efficiency, covering just 0.3% of the Earth's surface in solar panels would be enough to power all of civilization. And the frontier of our solar-powered future will be one of the least livable regions of the planet: the deserts. Deserts provide ideal conditions for solar power with their vast flat landscapes, abundant silicon, and constant sunlight. There are now proposals for massive-scale solar farms in the Sahara, capable of generating 4 times our current global energy usage. Covering over 20% of this desert could have dramatic side effects. The increased heat absorbed by the dark solar panels could disrupt global weather patterns and cause a spike in temperatures, especially at the poles. No matter how or where we get our energy, producing too much on planet will eventually be deadly. If our consumption grows at just 2% per year, we will use up all the energy available to Earth in as little as a few hundred years. But the real problem is that the waste heat from energy production at this scale would heat the Earth by over 20 degrees Celsius, which would make large parts of the planet uninhabitable. This will be the defining challenge of the coming millennia. How do we balance continuous energy growth with a safe, stable planet? By placing large-scale solar power arrays in space, we could capture uninterrupted sunlight nearly 24 hours a day, then beam the power down as lasers or radio waves. Orbital power systems would shed their excess heat into the cold expanse of space, instead of heating up our atmosphere. China is now planning a 1-kilometer wide solar array with the long-term goal of beaming gigawatt levels of clean electricity down from orbit. And a team from Oxford is planning an even bigger station, 1.7 kilometers across, called Cassiopeia, designed to be built in orbit. But collecting the power in space and beaming it down still has its own waste heat problems, as energy is still being added to the Earth's system. The solution is to move our power-hungry industries entirely into space. way, the energy can be collected, spent, and radiated completely outside of Earth's fragile system. And to get all this material into space efficiently, we need something incredibly audacious. Like a highway to the skies, a space elevator would open safe and easy passage to the next technological frontier, enabling the build-out of next-generation space infrastructure. To build it, a cable over 36,000 kilometers long would be lowered from a counterweight out in space, then anchored to a port station on the equator. A space station could then be positioned at geostationary orbit, at the point where the gravitational and centrifugal forces balance out. Laser or nuclear-powered rail cars would ascend the cable, carrying multiple tons of cargo at a time, which could drive launch costs down to under $100 per kilogram, 50 times cheaper than today. This could accelerate the mass production of solar power arrays, orbital data centers, research stations, and spaceports, laying the foundation for a new orbital frontier. But building this beanstalk to the heavens would be a daunting engineering prospect, requiring tether materials far stronger than anything that exists today. And moving human industry into space comes with its own major risks, especially space debris. Tiny pieces of scrap metal as small as a fleck of paint can tear through satellites and infrastructure, creating even more debris and causing a chain reaction of destruction known as the Kessler syndrome. To solve this, AI-guided laser systems could rapidly identify and deflect small debris. While larger pieces could be safely captured and deorbited. If we can neutralize these risks, then a space elevator could be just the beginning of an even greater vision of our planet's future. This is the crown jewel of space infrastructure, the orbital ring. This superstructure could become the backbone of our future civilization, a hub for everything from energy and transportation to climate management and tourism. In its basic form, a simple ring of wire would orbit the Earth around 200 kilometers up, with a stationary platform magnetically levitated above the spinning ring. It could be built as a free-floating structure or be tethered to the Earth at multiple points. Sky hooks and even hanging skyscrapers could dangle beneath the ring, serving as launch points, research hubs, or cities in the sky. Rotating the inner side independently would generate gravity through centrifugal force, making the area habitable and offering spectacular views. While no current technology can simulate gravity on the outer edge, it could still serve as a zone for microgravity industries and research habitats. An intricate network of rings could be built at different inclinations, offering rapid point-to-point travel almost anywhere on the planet. These layers could extend far outwards, even potentially networking with the moon. But the sheer size of orbital rings would pose their own dangers. A shadow the width of the ring itself would sweep over the Earth each day. For narrow rings, this would have little impact on ecosystems below. But wider rings, stretching over 1,500 kilometers, could cause major disruptions to the climate, blocking out the sun for an hour or more daily. Building one would be a towering engineering feat, as the ring would require tens of billions of tons of raw materials and constant active computer control to prevent collapse. To avoid impacting the Earth, the resources could be mined from asteroids. This may all seem like a far-off dream, but there are already proposals for prototype orbital rings that cost as little as $9 billion. People and heavy cargo could be transported along the ring networks to anywhere on Earth in only a few hours. Vast orbital cities and arable land could circle the planet and serve as new human frontiers. And with energy and heavy industry woven into the ring, we could scale our growth without disturbing the planet, preserving Earth as a sanctuary for life.